Now, when it comes to these scoop marks, is there any sort of idea or explanation on how they were made, either by the Egyptologists that are there?
Beneath the Egyptian sun, a slab of rose granite lies half-carved, its surface etched with curved gouges so precise they resemble machine cuts. For centuries, no one could explain how they were made, but a new clue from an ancient Turkish relief might finally reveal what the quarry marks, and the people behind them, were truly capable of. The impossible cut. Step into the Aswan quarry, and the first thing you see isn't just stone, it's contradiction. There, embedded in the rose-colored bedrock, are sweeping scoops and grooves that seem to have been peeled away rather than hammered. They dip and arc through the granite with such clean consistency that it feels less like ancient workmanship and more like modern machining. The largest of these marks curves deeply beneath the massive unfinished obelisk, as though something had tunneled beneath it with intent and control. These are not random scrapes left behind by casual laborers. Each hollow maintains a uniform radius, carved in patterns too precise to be dismissed as the result of dolerite pounding stones. Even amateur visitors who try the dolerite technique themselves find that it leaves nothing but dust, scratches, and bruised granite. Never scoops, never anything close to the strange concave impressions that snake across the quarry floor. What truly startles archaeologists is the placement of the deepest cuts. Some are located in tight spaces no human could reach easily, suggesting that whatever made them could bend, pivot, or apply force from awkward angles. It's as if the stone had been pressed by something guided, something capable of rotating, something that wasn't held by hand at all. And just like that, the ground beneath the obelisk stops being silent. It begins to whisper of tools no one can see and methods no one has fully understood, until now, what the experts said. For decades, mainstream archaeology held a reassuring line. These marks, they said, were the result of relentless patience and rudimentary tools. Workers, armed with dolerite pounders and copper chisels, would chip away at granite bit by bit. To split the stone, wooden wedges soaked in water would be hammered into narrow cuts. When the wood expanded, the pressure would supposedly crack the granite open. On paper, it sounded plausible, almost elegant in its simplicity, but on the ground, it collapses under scrutiny. Granite is one of the hardest stones on Earth. Copper is soft. When researchers attempt to recreate these cuts using the same methods, they're met with fatigue, frustration, and barely a scratch. Some manage to dig a few centimeters over several days, others accomplish even less. What they never produce is the type of smooth, sweeping gouges seen at Aswan. And then there's the shape of the marks themselves. Real dolerite impact leaves behind chips, not curves. Its strikes are chaotic, not measured. Yet the scoops at Aswan are unnervingly regular. The directionality of each groove follows a deliberate arc, consistent in both angle and depth. More like the path of a rotating blade than the blow of a stone ball. Experts tried to reconcile these inconsistencies with vague explanations. Perhaps ancient workers were just more persistent, more ingenious. But persistence doesn't defy physics. It doesn't sharpen copper into granite-cutting precision. And it certainly doesn't explain tool marks that behave more like the signatures of machines than the results of hand labor. This gap between explanation and evidence would eventually draw in a new wave of thinkers. Engineers, material scientists, and archaeologists unwilling to ignore what the stone itself seemed to be saying. The rise of alternative theories. As conventional theories began to fray under pressure, a new generation of researchers stepped in, not from archaeology departments, but from fields like material science, mechanical engineering, and fracture dynamics. Where historians saw a mystery, they saw a materials problem. If pounding stones and soft copper failed to explain the cuts, what would? One of the earliest alternative proposals centered on abrasives. Instead of striking the granite, ancient workers might have ground through it using quartz sand, hematite, or garnet, minerals harder than granite itself. When applied with enough pressure and motion, these abrasives could slowly erode the stone grain by grain. Some experiments using simple copper tubes filled with sand showed surprising accuracy, carving small circular holes with measurable depth. Still, this raised an uncomfortable issue: speed. The grooves in Aswan aren't just smooth, they're consistent over long arcs. Replicating those patterns with handheld tools would require not just precision, but rotational force, something difficult to generate manually. That's when theories of ancient mechanical devices began to surface. Bow drills, weighted flywheels, and even animal-powered systems were proposed. Some researchers pointed to spiral striations on stone cores, pulled from Egyptian sites like Giza, which bear uncanny resemblance to the grooves left by modern rotating coring drills. The implication was unsettling. Ancient workers may have developed devices that functioned with a level of engineering thought much earlier than anyone assumed. Others explored thermal shock, heating granite with fire, then cooling it rapidly to weaken internal bonds. It worked in theory, but often left brittle, unpredictable fractures, nowhere near the clean curves of the scoop marks. Each theory seemed to solve one piece of the puzzle, but failed to explain the whole picture. And so the question remained: what combination of knowledge and technique could account for all the evidence? The hybrid breakthrough. Everything began to shift when a multidisciplinary team returned to the Aswan quarry, not to test another tool, but to analyze the stone itself. Under magnification, the scoop marks showed something peculiar. Their interiors weren't gouged like chisel cuts or scratched like abrasion. Instead, the grain structure looked fractured, almost as if the stone had crumbled inward. The edges of the scoops resembled sheared clay, not carved granite. This observation led to a new hypothesis, one that didn't rely on any single method but a combination. What if the granite had been weakened first? What if the stone was heated using controlled fire, then doused with water to induce internal stress? At that critical moment, while still thermally shocked, an abrasive slurry of crushed quartz or garnet would be introduced. The mixture would infiltrate microfractures created by the heat, loosening the granite's bonds without shattering it. Then came the final piece, a guided scraping tool, not sharp enough to cut untouched granite, but perfect for removing softened layers in smooth, repeated arcs. This wouldn't require futuristic machinery. A wooden pivot arm, weighted and rotated with rope, could achieve the consistent movement seen in the quarry's concave marks. This hybrid method suddenly aligned with everything: the precision of the scoops, the absence of debris, the seemingly impossible access to awkward spaces under the obelisk. Even dolerite balls, once thought to be the primary tool, made sense. They could have been used afterward to break off remaining chunks. And in the residue left behind, researchers found traces of thermal alteration and mineral grit. It wasn't definitive, but it was enough to make one thing clear: the ancient Egyptians weren't just laborers. They were methodical, experimental engineers, working with a system far more refined than anyone had imagined: the missing machines. The hybrid breakthrough answered many questions, but one problem lingered: the mechanics. Could fire, slurry, and scraping alone account for such consistent arcs beneath the obelisk? The scoop marks followed paths too precise, their depth too uniform, their positioning too awkward to be the product of loose human effort. This led some researchers, like engineer Christopher Dunn, to propose something radical: a pivoting arm fitted with a rotating head, carving beneath the stone in controlled sweeps. The theory implied a guided rotary mechanism, not powered by electricity, but by ropes, counterweights, or rotational momentum. Such devices would require a conceptual understanding of mechanical leverage and torque, even if built from wood and stone. Critics called it speculative, pointing to the lack of physical machines recovered from the site. But the marks remained: clean, consistent, repeatable. And then, 1,000 miles away in southeastern Turkey, a carving emerged that deepened the mystery. In 2018, archaeologists at the site of Sayburks uncovered a 3,000-year-old relief showing a human figure operating what appeared to be a rope-powered mechanism, possibly a primitive drill or pulley system. It wasn't Egyptian, but it was proof that ancient engineers in the region understood how to apply rotational force using simple tools. This connection, visual, mechanical, and conceptual, suddenly made the impossible seem plausible. Maybe the Egyptians didn't need alien tech or steel machinery. Maybe they had what they needed all along: fire, stone, gravity, and a profound understanding of how to use them together. What if they were that advanced? If the ancient Egyptians mastered a process that combined thermal stress, abrasive chemistry, and guided mechanics, then the scoop marks are not an anomaly. They're a signature. Not of lost civilizations or forbidden technology, but of human ingenuity that we have consistently underestimated. It challenges a narrative many have long accepted, that ancient builders succeeded only through brute force and sheer numbers. But what if they didn't? What if their true advantage wasn't manpower, but method, the ability to observe, experiment, refine, and repeat those techniques at scale? It means that every massive obelisk, every mortise-cut stone block, and every precisely hollowed channel might not be a miracle of labor, but a triumph of practical physics, honed over generations. It also reframes the way we view ancient intelligence. These were not workers blindly following orders, but engineers and artisans deeply in tune with their materials. They didn't need blueprints. They had empirical knowledge. They didn't have machines, but they understood motion, heat, and force well enough to mimic one.
This is what they accomplished with tools that didn't survive. The real mystery isn't how they carved granite. It's how many of their other innovations we've mistaken for impossibilities.
The quarry walls at Aswan no longer whisper. They speak, not of forgotten empires or alien hands, but of people who mastered stone with fire, logic, and design. If that stunned you, share it. And if you want more, subscribe. We're just getting started.